Section: Introduction. We're excited to introduce you to the world of large language models, LLMs, like GPT-4 and Llama, which are becoming increasingly popular in a variety of AI applications. These models are used in everything from chatbots to document summarization, and even in autonomous driving and software development. However, as the demand for these models grows, so does the need for efficient ways to deploy and serve them. While tools like DeepSpeed and PyTorch can help optimize the training of these models, we've noticed that the interactive nature of many applications and the complexity of tasks like open-ended text generation can slow down the system. To address this, we've seen improvements in performance with frameworks like vLLM and research systems like Orca. But there's still a challenge in maintaining a consistent quality of service, especially when dealing with longer prompts. As more models and systems, like MPT Storywriter and DeepSpeed Ulysses, are designed to handle larger context windows, understanding how to efficiently process and generate text becomes crucial. We'll walk you through how this works in two phases: prompt processing and generation. If these phases aren't handled properly, the generation phase can be interrupted by the prompt processing phase, which can lead to service disruptions. That's why we're thrilled to introduce DeepSpeed-FastGen, a system that addresses these issues using a technique we call Dynamic SplitFuse. This system can offer up to 2.3 times higher throughput, twice the average speed, and up to 3.7 times lower latency compared to other leading systems like vLLM. DeepSpeed-FastGen combines the strengths of DeepSpeed-MII and DeepSpeed-Inference to provide a user-friendly serving system. Now, let's take a closer look at how text generation works. It involves two phases: prompt processing, where the user's text is converted into a batch of tokens to build a key value cache for attention, and token generation, where a single token is added to the cache and a new token is generated. As the text sequence is generated, the model makes multiple forward calls to generate the full text sequence. Two main techniques have been proposed to address potential issues during these phases. The first is blocked KV caching, which was introduced by vLLM to address memory fragmentation issues that can slow down LLM serving systems. This technique uses fixed-sized blocks of memory, or pages, instead of variable-sized chunks, which can increase system throughput by reducing memory fragmentation. The second technique is continuous batching, which was developed to improve GPU utilization. This technique involves waiting for multiple requests to process together, but it can lead to issues like needing to pad inputs to the same length or stalling the system to wait for a larger batch. To address this, recent advancements have focused on fine-tuning scheduling and optimizing memory efficiency. For example, Orca introduced iteration-level scheduling, which allows requests to join or leave the batch as needed, improving overall throughput. However, current systems still need to pause generation to process long prompts. That's where our new strategy, Dynamic SplitFuse, comes in. This strategy, which we'll discuss in more detail in the next section, allows for more efficient processing and generation of prompts. DeepSpeed-FastGen is designed to take advantage of continuous batching and non-contiguous KV caches, similar to existing frameworks like TRT-LLM, TGI, and vLLM. But what sets DeepSpeed-FastGen apart is its use of SplitFuse, a technique that dynamically decomposes and unifies prompts and generations to further improve continuous batching and system throughput. Section Summary. Large language models, LLMs, like GPT-4 and Llama are widely used in various AI applications, but the interactive nature of these applications and the poor arithmetic intensity of tasks like text generation pose challenges for inference throughput. Existing systems like vLLM and Orca have improved LLM inference performance, but struggle with consistent quality of service for long prompt workloads. DeepSpeed-FastGen overcomes these limitations by leveraging the dynamic split-fuse technique, offering higher throughput, lower latency, and improved tail latency compared to state-of-the-art systems. It achieves this by combining DeepSpeed-MII and DeepSpeed-Inference to provide an easy-to-use serving system. Section 3: Performance Insights. Before we delve into the specifics of Dynamic SplitFuse, let's first address three crucial performance-related questions that underpin its design. Firstly, what factors influence the performance of a single large language model, LLM, during its forward pass? To schedule effectively, we need to identify the key variables that the scheduling loop should manage. We've found that the composition of sequences in a forward pass, or the batch size in sequences, doesn't significantly affect performance. Instead, the raw number of tokens in the forward pass has a more substantial impact. This suggests that an efficient scheduler should focus on managing the number of tokens in the forward pass. Secondly, how does changing the number of tokens in the forward pass affect a model's throughput? An LLM operates in two main regions, with a sharp transition between them. When there are few tokens, the GPU's main challenge is reading the model from memory, so throughput scales with the number of tokens. However, when there are many tokens, the model's throughput is limited by computation and remains nearly constant. The model will run most efficiently if all forward passes occur in the region where throughput is saturated. Thirdly, how should we schedule a pool of tokens across multiple forward passes? We've observed that when inputs are well aligned, the token throughput curve is concave, meaning its second derivative is less than or equal to 0. In simpler terms, if we have a pool of tokens to process, the most efficient way to maximize throughput is to split them evenly between two batches. More generally, if we need to process P tokens over F forward passes, the best strategy is to divide them equally. Now, let's talk about Dynamic SplitFuse. This is a new strategy for managing token composition during prompt processing and token generation. It's used by DeepSpeed-FastGen to maintain a consistent forward size by taking partial tokens from prompts and combining them with generation. This approach, similar to one proposed in Sarathi, involves breaking down long prompts into smaller chunks and scheduling them across multiple forward passes. Only the final pass performs any generation. Short prompts are composed to fill a target token budget exactly. Even short prompts may be broken down to ensure the budget is met precisely and the forward sizes align well. This strategy offers several benefits. It improves responsiveness, as long prompts no longer require lengthy forward passes to process, reducing client latency. It also increases efficiency, as combining short prompts into larger token budgets allows the model to operate consistently in the high-throughput regime. Furthermore, it reduces variance and improves consistency. Since forward passes are of a consistent size and this size is the primary determinant of performance, the latency of each forward pass is much more consistent than in other systems. This results in a reduction of up to 3.7 times in generation latency. In terms of performance evaluation, DeepSpeed-FastGen provides top-tier LLM serving performance by using its blocked KV cache and Dynamic SplitFuse continuous batching. Our evaluation shows that DeepSpeed-FastGen achieves up to 2.3 times higher effective throughput, 2 times lower average latency, and up to 3.7 times lower tail latency compared to state-of-the-art systems like VLLM. For our benchmarking methodology, we use two main quantitative schemes to measure performance. We look at throughput latency curves, which are key metrics for production readiness. To measure these, we create multiple clients, from 1 to 32, concurrently and send requests to the server. We then measure the resulting latency of each request at the endpoint and the throughput by the total time taken to complete the experiment. Section Summary. The section discusses 3 performance insights that motivate the design of Dynamic SplitFuse. Firstly, the number of tokens in the forward pass has a greater impact on performance than the composition of sequences, allowing for effective scheduling based on the number of tokens. Secondly, the model's throughput is influenced by the number of tokens, with a transition from GPU bottleneck to compute bottleneck. Lastly, a concave token throughput curve suggests that evenly splitting tokens between batches maximizes throughput. Dynamic SplitFuse is a token composition strategy that decomposes long prompts, composes short prompts, and achieves better responsiveness, higher efficiency, and lower variance in forward pass size. In performance evaluation, DeepSpeed-FastGen outperforms VLLM in terms of throughput, latency, and tail latency. The benchmarking methodology measures throughput and latency using multiple clients and requests. Section: Effective throughput. Let's talk about the concept of effective throughput. Interactive applications, like chat apps, often have more complex needs than can be measured by simple metrics such as end-to-end latency. We're particularly interested in chat scenarios where a user sends a prompt, the system processes it and returns the first token, and then continues to stream tokens as they're generated. There are many points in this process where the user experience could be negatively impacted, such as if the first token takes too long to arrive or if the generation seems to pause. We suggest a service-level agreement (SLA) framework that takes into account both of these factors. Given that the lengths of prompts and generated texts can vary greatly, which affects computational costs, it's not practical to set fixed SLA values for throughput and latency. So, we define the SLA for prompt latency as the number of tokens in the prompt divided by 512 seconds, which equals a rate of 512 tokens per second. We also consider the average human reading speed and set the SLA for generation latency to 2, 4, or 6 tokens per second. Requests that meet these SLAs are considered successful, and the throughput of these successful requests is what we call effective throughput. We tested VLLM and DeepSpeed-FastGen on Llama 2.7b, Llama 2.13b, and Llama 270b on NVIDIA A100, H100, and A6000. In our throughput latency analysis, DeepSpeed-FastGen outperformed VLLM in both throughput and latency. It either provided the same latency with higher throughput or the same throughput with more responsive latency. For example, on Llama 270b with 4A100 by 80 GB, DeepSpeed-FastGen showed up to twice the throughput, 1.36 requests per second versus 0.67 requests per second, at the same latency, 9 seconds, or up to a 50% reduction in latency, 7 seconds versus 14 seconds, while maintaining the same throughput, 1.2 requests per second. In our effective throughput analysis, which considers both the latency of the first token and the rate of generation, DeepSpeed-FastGen provided up to 2.3 times higher throughput than VLLM. As we increased the number of clients, we initially saw an increase in effective throughput. However, as the number of clients neared the system's capacity, the latency also significantly increased, causing many requests to fail to meet the SLA. As a result, the effective throughput either plateaued or decreased at some point. We also observed a significant reduction in tail latency for token generation with DeepSpeed-FastGen. While both VLLM and DeepSpeed-FastGen had similar median latencies, VLLM had much higher latencies at the 90th and 95th percentiles. DeepSpeed-FastGen was able to reduce the 95th percentile latency by 3.7 times. DeepSpeed-FastGen also offers load balancing at the replica level, which evenly distributes requests across multiple servers, making it easy to scale up your application. We used 4A100 GPUs to run the Llama 270b model on up to 16 replicas across 8 nodes. The results showed nearly perfect scalability with DeepSpeed-FastGen. The throughput with 16 replicas reached 23.7 queries per second, a linear 16 times increase compared to a single replica. We also tested DeepSpeed-FastGen on other hardware platforms, including H100 and A6000, and observed the same performance trends as on A100. DeepSpeed-FastGen is a combination of several software packages that provide various components of the system, including the front-end APIs, the host and device infrastructure to schedule batches using Dynamic SplitFuse, optimized kernel implementations, and the tools to construct new model implementations. Section Summary. The section discusses the concept of effective throughput in interactive applications, specifically chat applications, and proposes an SLA framework to measure prompt latency and generation latency. The experiment shows that DeepSpeed-FastGen outperforms VLLM in terms of throughput and latency, providing higher throughput with equivalent or more responsive latency. Additionally, DeepSpeed-FastGen offers significant tail latency reduction for token generation and demonstrates scalability using load balancing. Section: Supported Models. In the initial release of DeepSpeed-FastGen, we support several Hugging Face model families, including Llama, Llama 2, Mistral, and Facebook Opt. These models utilize Hugging Face APIs in our backend to supply both the model weights and the corresponding tokenizer. We're planning to include more models in the future, so if there are any specific model architectures you'd like us to support, feel free to let us know. There are several ways to deploy these models. For a quick start, you can use the non-persistent pipeline deployment, which is easy to set up with just a few lines of code. This type of deployment is temporary and lasts only for the duration of the Python script you're running, making it suitable for short-term interactive sessions. For long-term and production applications, we recommend a persistent deployment. This involves setting up a lightweight gRPC server, which can be done with just 2 lines of code. This server can handle multiple client queries simultaneously, thanks to the built-in load balancer from DeepSpeed-MII. To make the installation process easier and reduce lengthy compile times, we distribute a pre-compiled Python wheel that covers most of our custom kernels through a new library. This library is compatible with NVIDIA GPUs with compute capabilities 8.0+, Ampere+, CUDA 11.6+, and Ubuntu 20+. In most cases, you won't even need to be aware of this library as it's a dependency of DeepSpeed-MII and will be installed with it. We're thrilled to share the alpha release of DeepSpeed-FastGen. To get started, visit our DeepSpeed-MII page. DeepSpeed-FastGen is part of the larger DeepSpeed ecosystem, which includes a variety of deep learning systems and modeling technologies. For more information, check out our blog posts, tutorials, and documentation. You can also follow us on social media for the latest DeepSpeed news. We welcome your contributions, so feel free to report issues, contribute PRs, and join discussions on our page. Looking ahead, we plan to improve performance, support more models, collaborate with partners on new hardware backends, and release performance benchmarks. If you appreciate our work, please consider starring our repositories. We'd like to express our gratitude to the entire DeepSpeed team for their hard work on developing, debugging, testing, and releasing the DeepSpeed-FastGen software. We also appreciate the contributions of various open-source community projects, including Hugging Face, VLLM, and Hugging Face TGI. We've used the Flash attention kernels extensively in our system, and we're grateful to the developers for their excellent work. We also want to thank the developers of kernels that we've used in our MO kernels.